Hello. So we want to consider the Green's theorem. I want to consider the Green's theorem. So first, let me explain this figure over here. We are supposing that C is actually a simple closed curve which forms the boundary of a region S in the XY plane. And so let C be oriented so that traversing C in its positive direction keeps S to the left. That is the counterclockwise orientation. And the corresponding line integral of that will around C will be denoted by the whole of this. Will be denoted by the whole of this. So the whole of this explanation will help us actually to explain the Green's theorem. And so well, let's see be a piecewise smooth, simple closed curve that forms the boundary of this region S in the XY plane. And we'll let our MXY and then NXY, which are continuous and have continuous partial derivatives on S and its boundary C. If you have those ones, then the whole of this will hold for the Green's theorem. The whole of this will hold for Green's theorem. Remember that C is a closed simple curve or a simple closed curve. That's fantastic. So this gives us the Green's theorem. This gives us the Green's theorem. Very important. Now, remember our M is here, and we'll differentiate the M with respect to Y. Our N is there. We shall differentiate the N with respect to X. And then from there, we shall actually move on. All right. So let's look at one of the questions over here. Let's look at one of the questions over here. So let's see be the boundary of the triangle with vertices 0, 0, 1, 2, and 0, 2. Calculate our expression here. So we want to calculate it. So first, we need to sketch it. So we have our 0, 0, and then we have 1, 2, we locate it, and then we also have our value over here. So this is the triangle that we're actually talking about. So C, C1, C2, and then C0. Okay, so basically that is how the sketch goes. So you can look at the sketch very well. If you look at the sketch, all right. Look at the sketch very well. Great. So we are now going to use the Green's theorem. And so we have our expression. The whole of this is our value M, and this is our N. So M dx, N dy. So what we are doing is that we are differentiating the whole of this. We are differentiating the whole of this with respect to y, and we shall differentiate this with respect to x. So 2y differentiating that partial respect to x will give us 0 here. Then we come here, differentiate the whole of this respect to our y. So when we do that, then we shall get 4x squared. So that is why we have this. Then within the interval, remember that C1 gives us our y equals 2x, and then we move on to our y, the final also give us 2. Then the x move from 0 to 1. X we move from 0 to 1. So from this, from 0 to 1 for the x, and then the y along the line is that is also important that right away. So we are picking the inner one, we differentiate respect to y, and so we get 4x squared y with our minus. Then we slot in the interval. So first we put in our 2x. So 2x here will give us negative 8x squared. Sorry, 8x cubed, because we are subtracting the base from that. So we get minus minus, so 8x cubed. And then the upper, put in 2. So we shall get negative 8x squared. We shall get negative 8x squared here. And then when we do that, basically, we move on to this step and simplify it. All right, so we get here, now that we put in our value. So we're also going to integrate with respect to x. We add 1 to this, we get 3, we divide this by that. So 8 on 3, our negative comes x cubed. We add 1 to 3, we get 4. So 8 on 4 gives us 2, and then our x raised to the power 4. We now slot in our intervals. And so when we do that, we shall get 8 on 3 plus 2. Going through the normal way, our LCM, we shall get negative 2 on 3. And so that does it for the Green's theorem. That does it for the Green's theorem. So look at this again, Green's theorem. I explained using this figure. See, it's a simple closed curve region S that actually is giving us the boundary. That gives us the boundary. Yes, where C is actually the boundary of the region S. And so the whole of this gives us the Green's theorem. And we have used that in a question and we've solved that. So mxy and then nxy. So m is a function of x and y, and then n is also a function of x and then y. Great. So this is the question that we just solved using the Green's theorem. Then we got our value to be 2, negative 2 on 3. Negative 2 on 3. So there's an exercise here. I want you to try that. So use Green's theorem to evaluate the line integral. Line integral given where C is the ellipse. That. Great. Now we are moving on to the Gauss theorem. We are moving on to the Gauss theorem. So we say that let F be equal to this, be a vector field such that M, N, and P are continuous first order partial derivatives on a solid S with boundary del S. And so if our N denotes the outer unit normal to del S, then we have this given as the value or the theorem that we are actually looking for. So look at what we have in the rectangle. Look at what we have in the rectangle. That gives us the Gauss theorem. That gives us the Gauss theorem. So we have the Gauss theorem here, the X, then our S. Now, so what we are saying is that if we have our N being equal to this, where our alpha, beta, and gamma are the direction for N, then our F dot N will also give us this. So the Gauss formula also becomes the whole of this expression. Let's look at that. So we have our del S. We have our del S. Good. We have our del S. Then that gives us the double integral, gives us the triple integral over S. That gives us the whole of this expression. So let's take note of that. Now, so we want to look at some examples. Verify Gauss's theorem for F equals xi, yj, and then zk, and where our S is equal to the given interval by independently calculating f and ds, and then our b. So we have this and then b, right? So we want to look at the first aspect. And so over here are the legs. On the legs, we have our n being equal to this on A. And then our f dot n will give us the whole of this on A. Remember this one from the question, we are saying is less or equal to a squared. So that will be a squared on A, and that will give us our A. All right, so right away from there, we can now calculate our f dot n ds. We have our A ds, and this gives us the surface area. And so straight away we get our 4 pi a cubed. Now we are now moving on to finding our Green's theorem. Fantastic, very, very important. Okay, so the Gauss. We are now going to compute the Gauss theorem. Sorry, so we have our div f, and that will be given by this. So our triple integral div f, and then dv. Now we want to remember that finding our div f will give us 3. And div f will actually give us 3. And so when we get a 3, we can now be using it for our solution. Okay, and so Now that we've gotten our 3, now I have our triple integral over s dv. We want to remember that we're actually dealing with the volume. So straight away, we get our value here. And then when we simplify, we shall now get our 4 pi a cubed. Okay, straight away, we've been able to use that to compute our value that we are interested in. Now, we want to compute the flux of the vector field given this way across the surface of the rectangular solid S determined by this interval. So X is between this and that, Y giving us this, and then Z giving us the following. Okay, straight away, so using the Gauss, we write it down. So we have our value here being equal to that. Now remember that we give this here. So we are using this concept, del m del x, del n del y, del p del z, dv. So that is what we are using here to simplify that. Okay, so straight away we have it this way. So this will give us 2xy. This will also give us, because we are doing that with respect to y, that gives us 0, and over here, z, so we get 3yz squared with our dv. So the next step is that we have the intervals given in the question, so we do so as has been indicated using the intervals given. So dz dy dx. So we shall pick this first, respect to z. When we do that, remember this is z. So once we do that, we shall get our 2xyz, and then when we also get to this point, because we are actually doing our integration, then basically we also add 1 to this one, and then we divide by 3. And then from there, we put in our values. For 0, everything will go to 0. And then for our 3, we'll do that. And then that'll be the upper. So we shall get our 6xy plus 27y. And then we now move on to this integral with respect to y. So when we do that, we add 1, we divide by 2, and then here we also add 1, divide by 2, and then we slot in our interval for 0, everything goes to 0, and then we now deal with our 2. So when we do that, we shall get 12x plus 54. We now move on to the x, so that's the last integral, and so we add 1, we get squared, we divide 12 by 2, so 6x squared. This one will give us 54x. Now slot in our values. So 0, everything goes to 0, 1. So we get 6, and then plus our 54, and that gives us 50. Great. So that does it for this one. So let's look at so that does it for the Gauss's theorem. That does it for the Gauss's theorem. So very important for what we have actually done today for that. Okay, so we go through. All right, so use Gauss's theorem to calculate my expression. Yes, so we have the first question, and then the second question, then the third question. So these are the questions, 3 questions. Question 1, question 2, question 3. Fantastic. We are moving on to the Stokes theorem. I'm moving on to the Stokes theorem. So Stokes' theorem, we are saying that let S, the Lex and N be as indicated already, and suppose our F is equal to that. It's a vector field with M, N, and P having continuous first order derivatives on S, and is bound to the Lex. And so if T denotes the unit tangent vector to the Lex, then we have an expression here giving us the Stokes' theorem. So F dot T ds close interval del x give us a double integral over s del f dot n ds. All right, so this is the Stokes theorem that we are actually considering. And so we want to look at an example. Verify Stokes theorem for our f given as this. If s is the paraboloid zx squared y squared with the circle s squared y squared equal to 1, where our z is also equal to 1. So look at the question very well. Look at the question very well. All right. As, and then we have z equals 1 acts, and then all giving us its boundary. All right, giving us its boundary. So we look at the solution. We look at the solution. So we have curl f. Curl f. And so right away, we know that finding our curl f, we have our ijk, and then del x, del y, and then del z. And so we go back to our f, and so we have x, our y, and then we have our y, next x, and then yz. So put them there. Okay. So when we take our time and find the determinant, we shall get z I0j minus our 2k. So we've been able to complete our curl f. Then it means that our whole expression will give us this. And our ds, the s becomes the x dy. So straight away, going back to our expression, so after dotting, then that takes us to, just remember that we have it this way, n dot ds, okay, and we know how to find the n. So straight away, we get our square brackets, 1 minus our values over here, 0 to x minus 2 dx dy. All right, so we get a negative 2 coming out. Then with our double integral, so our xz, and then we shall also get our plus 1 over here. Very, very important. Our dx and then dy over r. So look at the process, how the whole thing was actually done. Look at the process and how the whole thing was actually done. All right. So if you could see this one, this will be 2zx. And then this will go to 0, and this and that also give us minus 1. And so, right. So look at this carefully. And then we can actually simplify that. So let's look at this, see how the whole thing has been done. See how the whole thing has been done if you actually make a headway of the explanation that has been given. So take your time and look at it. Take your time and look at it carefully, how the whole thing was done. Look at it carefully. Look at the computation, the explanation given, how the whole thing has been done. Look at it carefully. Okay. So try and analyze it. Take your time. Analyze it very well. That is from this step to this step. I want you to take your time and look at it carefully and see how we simplified it. So that does it for this one. Good. So we normally get negative z2x. So this will give us that, and then that takes us here. All right. Fantastic. Okay. So it takes us here. Now, when we get to this point, remember we have a double integral. So we actually want to look at that, and then we'll move on with it. Okay. All right. So we are now going to deal with dx. And remember, that will be the interval 0, 1. And then we also want to this one. Then so this one we are actually switching on to the appropriate usages. And so when we do that, we now remember we have our value s squared, y squared, and that one you can straight away get a value on it. So you look at from this step to this point, you look at it carefully and see how we moved from that step to this step. Just look at it and see. This one, what comes to mind? What comes to mind here? What comes to mind here? You can remember that this one can just give us our r squared. And the whole of this will give us our r cos theta. And so that is why we have our r cubed cos theta, the polar coordinates plus our 1. And so we have actually, moved on to that aspect. Okay. So from there, we can now take our time, and then our boundaries 0 to that our intervals, and then 0 to 2 pi. Okay, so from here, we are actually doing our integration. Fantastic. Okay, so we take our time and then do the integration with respect to our r. When we do that, then we slot in our value 0 to 1. So that will land us on here. So take your time and fill the missing link. Now we actually left with our theta, and so we are going to integrate respect to theta. When we do that and put in our intervals, we get negative 2 pi, negative 2 pi. So this is the diagram, the sketch of the diagram. So our n, the s, our z axis, our x axis, and then our y, and this region. So you take your time and go through. If you have any questions, you can, yes, let's have them. Okay, so this one too, we've looked at the Stokes theorem. We've looked at the Stokes theorem, and we've actually solved the question under that. All right, so this is the exercise that I want you to also do. The exercise I want you to do. Okay. So use Stokes' theorem to calculate our expression. So question 1, question 2. Fantastic. Thank you so very much. We dealt with the 3 important theorems. We dealt with the Green's theorem. And then we actually moved on to the Gauss' theorem. And we've now finished with the Stokes' theorem. Continue to try your hands on lots of questions. It needs patience and some kind of meticulous solution of a number of questions, and you will make a headway. Thank you so very much for your attention. Have a blessed day. Bye-bye.